Question number 1. A student holds a thin strip of paper below his lower lip and blows air horizontally over it. If the surface area of one side of paper is A and the mass of the strip is simple m, the speed v with which the air should be blown in order to keep the strip horizontal. They have given density of air as rho. I will consider the strip of paper and 2 points below it and above it. I will consider this point as A and this point as B. We can use Bernoulli's principle between point A and B. Pressure plus kinetic energy per unit volume, half rho v squared plus h rho g for point A should be equals to pressure plus half rho v squared plus h rho g for point B. We know that A and B are in the same horizontal line, therefore there is the same h value from gravitational potential energy 0 level. Then I will use pressure of A as PA. Velocity at point A should be 0 because of the air blow should be in the upside of the strip of paper. Pressure of B, PB, half rho v squared. Now I will subject pressure difference PA minus PB equals half rho v squared. Then this is the relationship for pressure difference, and we know that to keep the strip horizontally, weight of the strip should be equals to upward force due to pressure difference. Upward force due to pressure difference should be equals to weight. Then we can use, you know that pressure is force divided by area. Then we can subject force. Force is pressure difference into area. PA minus PB multiplied by area equals to mg. Area means perpendicular area. Perpendicular area is area of the strip because of pressure is acting in this direction. Pressure difference. Then we know that PA minus PB, pressure difference is this value, half rho v squared into A equals mg. Now we have to subject V term. V equals half rho v squared equals mg. Then we can subject V value 2 mg divided by rho root. Answer for the question number 1 is 1. When subjecting, we have to get this A term to the left hand side. Then 2 mg over rho A root. First one is the correct answer. Then question number 2. A river having a constant width is flowing steadily at a certain constant speed, except in a certain region. If the speed of flow in the region is found to be lower, then which of the following curves best represents the variation of depth of the river along the length of the river. According to Bernoulli's principle, if the velocity is a small value, cross-sectional area should be a large value. Because of we know that for a steady flow, VA product should be constant. VA product should be constant. Velocity into cross-sectional area. Now they have given the river having a constant breadth. Therefore, we can consider it is like this. There is a constant breadth. But velocity at a certain path is a small value. It means when considering cross-sectional area, the cross-sectional area of that part should be a large value. Therefore, depth should be a large value for the corresponding region. Then we can get depth should be increased for that region, and there is a constant depth for other regions. Depth with distance. Then this one is the correct answer for question number 2. Then third question, which of the following cannot be explained using the Bernoulli's principle? First answer, curving of the path of spinning ball while moving in air. Yes, we can explain it by using Bernoulli's principle. Second one, upward lift on aeroplane. We can explain it by using Bernoulli's principle. Third one, action of spray pump. It also a result of Bernoulli's principle. Fourth one, motion of a rocket in space. No, it can't it can't explain by using the Bernoulli's principle, because of we know that it is moving according to Newton's third law. Fifth one, rise of smoke through a tall chimney. We can explain it by Bernoulli's principle. Then correct answer is 4 for the question number 3. Fourth one, airflow through the tube PQ at a constant rate. Two ping pong balls are levitated in equilibrium above the tiny vertical tubes X and Y, through which the air escapes. The height of two balls from the tube at equilibrium are Hx and Hy respectively. Which one of the following statements is true? We have to compare Hx and Hy values. Then we can get the pipe piece like this. There are two regions with a small cross-sectional area and large cross-sectional area. In this part, cross-sectional area is a greater value. Area is greater than area of this pipe. Ax, Ay. And we know that if there is a steady flow, AB should be constant. It means velocity of x should be less than velocity of y. According to Bernoulli's principle, if the velocity is a small value, pressure should be a large value. Therefore, pressure at x should be greater than pressure at y. Pressure is a large value. To maintain this pressure, there will be a water height in these two pipes. Px is a large value. Therefore, height of x cube should be greater than height of y cube. Then Hx we can get if airflow from P to Q. Hx should be greater than Hy. Then first answer is correct answer for the question number 4. Question number 5. A non-viscous incompressible fluid of density rho flows through a pipe at speed of v. Two manometers A and B are connected to the pipe as shown in the figure. If the pressure measured by manometer A and manometer B are P1 and P2 respectively, the speed V of flow is given by. They have given pressure reading for manometer A is P1, manometer B is P2. Then considering this point and this point, we know that velocity of flow for this point is V. It is equal to the velocity of flow in the tube. And velocity for this point should be 0. It will not move through this pipe because of it is a closed one. There is a manometer liquid in this part. Now we can use Bernoulli's principle between this x point and y point. Y point is in the small tube. Then using Bernoulli's principle, we can write pressure plus half rho v squared plus h rho g for point x for this point should be equal to the P plus half rho v squared plus h rho g for point y. And we know that these x and y points are in the same horizontal level. Therefore, h rho g term should be a constant value for both terms. We can cancel out it. We can get pressure at x P1. It is the reading of this manometer with this plus half rho v squared. V is the velocity of point x, then we can use half rho v squared. Pressure at point y is Py. P2, it is the reading of second manometer. And we know that velocity for y point should be 0. Now we have to subject v term. We can bring P1 term to the right hand side. Half rho v squared equals P2 minus P1. Then we can subject v term to P2 minus P1 divided by rho root. 2 P2 minus P1 divided by rho root. Then answer is 1 for the question number 5. Then question number 6. The figure shows an underground cave with two small openings at A and B. The wind is blowing over the cave. Pressure and velocities of air at A and B are PA and VA and PB and VB respectively. We have to compare pressure and velocity for given A and B points. A point is this one, B point is this one. We know that they have given velocity for point A is VA, velocity for point B is VB. There are some problems related to answers, I will explain it. Relative to this shape, the airflow will be like this. We can draw flow lines like this. In considering flow lines, it is the shape, it is due to the shape of given cave. Flow lines at this space B should be, the gap between flow lines at B should be less than gap between flow lines at A. Therefore, velocity of B should be greater than velocity of A. We can consider it as a decreasement of cross-sectional area. B should be VA because of the shape of the object. Then velocity of A is a small value. Then pressure of A should be a greater value. PA should be greater than PB. It should be the answer, but in the given answers, there is no correct one. You can mark it. VB should be greater than VA, PA should be greater than PB. And therefore, there is an airflow from A to B because of air or any fluid is flowing from high pressure to low pressure. Therefore, there is a flow from A to B. Then question number 7. A water flow system consisting of manometer tubes A, B, C and D is shown in the figure. Water enters the system at X at constant rate and the pressure greater than the atmospheric pressure and leaves at Y. Is the height of water levels not indicated in the diagram. In manometer tubes A, B, C, D are HA, HB, HC and HD respectively. Then we have to compare H values. Again we have to use AV, area into cross-sectional area into velocity should be constant for a steady flow. When comparing given parts of tube, the smallest cross-sectional area is for C part. We have to consider area of flow tube. There are 4 parts and the smallest area for this part. It is equal to the area of this part. Therefore, velocity for these 2 parts are smaller than other parts. Therefore, when velocity is greater than other parts, when velocity increases, when area decreases, velocity should be increases. And according to Bernoulli's principle, when velocity increases, pressure should be decreased. Then we can observe smallest pressure at C and D. Therefore, we can get height of liquid column in tube C and D should be equal. HC should be equals to HD, but these two heights are the smallest height when comparing A, B, C, D. And no, A is this part, B is this one, C is this part, D is this part, not this one. Therefore, we can consider point C has the smallest cross-sectional area. Therefore, highest velocity could be obtained for point C. Velocity increases, then pressure decreases. Therefore, the lowest pressure at point C, HC should be the smallest value. And then cross-sectional area of part A is greater than C. Therefore, HA is greater than HC. Cross-sectional area of D is greater than A. Therefore, HD is greater than HA. And we can observe highest value, largest value of H for B tube. HB, HD, HA and HC. We can get fifth answer is the correct answer for question number 7. Then 8. A non-viscous and incompressible fluid flows to a tube in which the cross-section is varying as shown in the figure. The variation of pressure along the axis OX is best represented by cross-sectional area is constant for this part. Therefore, velocity constant, then pressure should be a constant value. Pressure. And velocity is cross-sectional area is decreasing for this part. You know that when velocity decreases, when cross-sectional area decreases, velocity should be increase with distance. Velocity increasing. Velocity is increasing. Therefore, pressure should be decreasing with time, with distance. Pressure should be like this. And after this point, there is a uniform tube. It means there is a constant value for the cross-sectional area, then again pressure should be constant. Then fourth one is the correct answer for question number 8. Question number 9. Water drains through an operating of area A1 in a container of cross-sectional area A2 as shown in the figure. If the motion of the water surface in the container is not ignored, the speed V at the water drains is given by. Velocity at this phase is V. I will consider velocity at this point as V1. Then we can use Bernoulli's principle between this X point and Y point. Before using Bernoulli's principle, I will use continuity equation A1 V1. For point X and Y, A1 V1 should be equals to A2 V2. Cross-sectional area for this part is A1, it is given equation. Sorry, A2, it is given in the question. velocity V1, I have considered it as V1. Cross-sectional area for this part is, in the diagram they have marked A2. The water drains to an operating of area A1 in the container of cross-sectional area A2. Yes. We can consider this area for the Y point A1, velocity V. Now I will subject V1, A1 V divided by A2. I will consider it as the first equation. Then we can use Bernoulli's principle between x and y. P plus half rho V squared plus h rho G for point x should be equal to P plus half rho V squared plus h rho G for point B. And they have marked difference of height, simple h. I will consider this level as the potential energy zero level. Therefore, height for point y should be 0. H rho G term should be 0 for point y. Then I will substitute given algebraic terms. Then we can get pressure at point x is atmospheric pressure. You know that point x is open into the atmosphere. Therefore, pressure at point x should be atmospheric pressure. And point y also open into the atmosphere. Therefore, pressure at point y should be atmospheric pressure. There is a constant pressure for both sides, atmospheric pressure. Then we can cancel out pressure term. Now, half density rho, velocity at x v1 squared plus height relative to potential energy zero level is h for the point x, h rho G equals to half rho V squared. Now we can substitute, we can cancel out rho term and we can substitute V1 value by using this equation. Half V1 squared, then A1 B divided by A2 squared plus HG equals to half V squared. Then I will bring all V terms to the right hand side. Hg equals to half V squared is a common factor. We can get when dividing half V squared by half V squared 1. When dividing this term by half V squared, A1 squared divided by A2 squared. Now we can subject V value 2Hg divided by 1 minus A1 squared over A2 squared root. Then first answer is the correct answer for question number 9. In question number 10, figure shows the bureau of some animals living underground. The animals maintain the shape of two entrances A and B to the bureau different from each other, and because of this air density 1.3 blows past the opening at different speeds 8 and 2 as shown in the figure. If the opening area, openings are at the same level, the difference of air pressure between openings at and the direction of air moved in bureau. Again we have to use Bernoulli's principle. There are 2 points this one and this one. I will consider A and B. Then we can use Bernoulli's principle between A and B for the airflow in this direction. They have given velocity. P plus half rho V squared plus H rho G for point A should be equal to P plus half rho V squared plus H rho G for point B. Now they have given that there is a same height for both points. We can cancel out H rho G in the same horizontal line. Pressure at A plus half rho 1.3. Velocity at A is 8 squared equals to pressure at B plus half density 1.3. Velocity at B is 2 meters per second, then 2 squared. We have to find the pressure difference. Then I will subject PB minus PA because of pressure at B is the greater value. We know that when pressure is greater than B because of velocity of B is less than A. Then PB minus PA half 1.3. These two terms are common factors. Then 8 squared minus 2 squared. PB minus PA half 1.3. We can write this term by using this bracket by using factors. There is a difference between two square terms. Then we have to get 8 plus 2 10. 8 minus 2 6. Now we can simplify it. 2 divided by 2 1 3. 3 into 13 39. 3.9 multiplied by 10 39. Then we have to get 39 Pascal. High pressure is at B. Therefore, flow will be from B to A. 39 Pascal and from B to A. The third one is the correct answer for question number 10.